I'll explain in detail what we mean by thermal resistance later on. Just hang on to this particular one. So next we want to look at again another rectangular slab. Consider a slab of isotropic. So what is the meaning of isotropic? Yes, constant what? No pressure. It's a good attempt, but it's not correct. Yes, isotropic, constant what? So you have forgotten all this. I told in the earlier, in the beginning of this class. So isotropic means that, you see, I have told you, thermal conductivity is a property of a material which gives the ability of a material to conduct heat. And thermal conductivity always changes with temperature. Temperature increases, thermal conductivity will be increased. So for some certain fluid or material, the thermal conductivity is going to decrease with respect to temperature. You understand me? But I've told you in this class, we are going to assume that thermal conductivity for all our purposes is always a constant parameter. So even if the temperature changes, we assume the thermal conductivity to remain constant. And any material whose property or the thermal conductivity remains constant throughout, even the temperature is changing, is said to be an isotropic material. So isotropic means the property of the material remains invariant with temperature. It means it doesn't change. It remains the constant. So thermal conductivity for the water equals to 10. So throughout the history of the water, temperature is increasing, the thermal conductivity remains constant. You understand? So then that's what we refer to as isotropic material, invariant. Okay, so all the definition is there, it's clear. Isotropic means having properties that are identical in all directions. So such as thermal conductivity, all directions remains the same. Okay, in this way. So there we have again another solution, general equation for conducting with heat generation. So this time we are going to consider heat generation, okay, in the rectangular slab. But then it is a steady state, and at the same time it is one dimension. One dimension means this and this goes out, so you have this is also out of the equation, so eventually we'll be left with these two equations only. So this is similar to what we have just discussed now, but this time we are assuming only two parameters. So this and that are equal to 0. So now we need to solve this also. So to find the temperature distribution if there is heat generation. Okay, so now here we rearrange the equation. Okay, so we have described it by the x equals to minus q, okay, divided by k. So again we'll integrate this function, that's the t over the x. We integrate this, we get this times x plus a constant. So again we integrate this, we get that. We integrate that, x squared divided by 2k. Again we have c1 plus c2. So now we need to apply boundary conditions to determine c1 and c2. So after which we will substitute into the general equation. So now that at x equals to 0, okay, now we will have this 0, t1 equals to c2, and at x equals to l, okay, so then again t2, so c1 becomes equals to the whole of this. Okay, so now you substitute c1 and t2 into the general equation. So eventually we will be left with this equation. So this is the general equation when there is heat generation within the element. Now, if we want to determine the heat transfer within the element by virtue of this temperature distribution, then it is going to be like this. So if you are asked to determine the heat transfer after the final solution has, or the temperature distribution, we will have to differentiate this function again. The final solution is this. We have dx. It's a function of x equals to minus q divided by what? So 2kx squared. Then plus we have delta t divided by l divided by l only plus. So that is being q divided by 2k. Q divided by 2k times that times. Okay, so now plus t1. Okay, so if you want to find the heat flux using this equation, all that you need to do is that you know q equals to minus k dt over x. So heat flux I divide it by area. By area this becomes small q equals to minus k dt over x. So I'm going to differentiate this function. So dt over the x of this function is v. I'll get 2 minus 2q x divided by 2k. You agree with me? I'm differentiating this with the circle x. So that is 2k q x divided by 2k. And if I differentiate the whole of this, so the whole of this is a constant. So I differentiate with respect to this, so it's the same. So I'll have delta t divided by L plus Q divided by 2k times L. Okay, so then this is 0. So this is the final solution. So what we will do is substitute this into that. So it means my heat flux equals to, this is minus, this is positive, this becomes minus. Okay, so I'll have, and this will cancel out. So eventually I'll have k into brackets. So q dash divided by k, right? So what I did, yes, divided by k. So I'm multiplying k by the whole of this. Okay, so then again it multiplies plus, is it plus or minus? Minus, right? So the minus sign is here, so we have all this times k and minus. So the minus enters, this becomes positive, this minus, yes. So I'll have delta t divided by L minus q divided by 2k times L. Yes? Any problem? This is the k.
X.
Where? Oh yes, there should be x. Where? Okay. So this is the general, this is the heat flux related to the conduction. Okay. Yes, so we have minus k dt over the x. So the solution for that is this. Okay. Okay, so now we have some experience on how to calculate. So we will be looking more details into different solutions or different questions related to this heat transfer later on. Now before I start with this, I want us to discuss this question. So the past year question, which I told you to. Can I delete this now? Okay. So let us discuss the past year question which I sent to you. So December 2016. So I told you to send me the soft copy. You didn't do that. It's already there? Okay, so let's see.
Let's wait and see.